Greetings. So welcome to today's class. Let me start off with a couple of clarifications before we start today's discussion. The first one is on this homework problem which I gave you. Please recall the notation that we are using. We are essentially considering C alpha F to be the cornering stiffness of each front tire. Okay, so that is why this KV, right, the understeer gradient will be WF by 2 C alpha F minus WR by 2 C alpha. Okay, so let me go. Yeah, here it is, right? So you can see that it is written in this form. So in some references, they would just write WF by C alpha F minus WR by C alpha R, with the understanding that the C alpha and C alpha F and C alpha R will be the values for both front tires and both rear tires combined. Okay, so as I discussed when we derived the dynamic bicycle model, in our discussion in this class, I am assuming I am taking them to be the cornering stiffness of each front tire separately and each rear tire separately. Okay, so that is why we are having that factor 2 coming into picture. Okay, and consequently, the data I have given you in this table corresponds to the value of the cornering stiffness for each front tire and each rear tire. Okay, so you need to substitute accordingly in that formula. So you need to use KV equals WF by 2 C alpha F minus WR by 2 C alpha. Okay, so I hope that clarifies that question. So let's move to our discussion. So if we recall, we were looking at braking, and we are going to start off with braking dynamics in today's class. What we are going to do is that, like, in this analysis, we are going to look at various forces that act on the vehicle during the process of braking and how one could relate them and get equations of motion, right? So to characterize the braking process. Okay, so that's what we are going to do. So let me start off with a few notations. So what we are going to do is that, like, we are going to essentially use capital W once again to denote the vehicle weight. Okay, weight of the vehicle. Okay. The total weight of the vehicle, and we will essentially take A to be the deceleration of the vehicle. Okay, so in general, A is the acceleration, and when the vehicle is being decelerated, it will have a negative value, right? But in this derivation, we will essentially take A to be the deceleration, so that's going to have a positive value. Okay, and then what we will also do is the following. We will assume, without loss of generality, that the vehicle under steady is going on a gradient of grade angle theta s. Okay, so theta s is what is called as a grade angle. And as we know, this W is going to be equal to M times G. Okay, so typically, as we also discussed, in vehicle dynamics terminology, the mass is called as gross vehicle weight. Okay, GVW of the vehicle is indicated in kilograms, and that is the value of M. Okay, so but the weight of the vehicle is M times the acceleration due to gravity. Okay, so that's something we need to keep in mind. Okay, so now let's go and look at the free body diagram of a vehicle during braking. So just let's refer to the schematic. Let's identify all the forces that have been indicated here. So to begin with, this is the vehicle's CG. Okay, and without loss of generality, we will assume that the vehicle is moving up the gradient. Okay, so the vehicle is moving on the gradient in this direction, and it is being braked. So consequently, A is the deceleration of the vehicle. Okay, so that is what it is. Okay, so A that we see here is the deceleration of the vehicle. Now we can see that W is the total weight of the vehicle, and we are essentially traveling on a grade of angle theta s, as we discussed. So consequently, what will happen is that this W will have two components. Okay, so one component will be normal to the plane, and one component will be along the plane. Okay, so what are these two components? So this component will be equal to W cos theta s. Okay, this component which is along the plane will be equal to W sin theta s. Okay, so that's also something which all of us know, right? Yeah. Now, let us say the contact point, the center of the contact patch of the front tire road interface, let's call it as point A. And this point, we call it as point B. And the distance between point A and point B, as we know, is essentially the wheelbase of the vehicle. Okay, so as we already know, capital L is the wheelbase of the vehicle. Okay. And along the longitudinal direction, we consider that the center of gravity is located at a distance of L1 from the front wheel contact point center, contact path center, and a distance of L2 from the rear wheel contact point center, or point B. So consequently, we know that L1 plus L2 is equal to capital L. And I think I would have mentioned this again before. So different textbooks will use different notations for characterizing this L1 and L2. I think when we did lateral dynamics, we would have called it LF, LR. Some textbooks will call it as L1, L2. Some textbooks will call it as A and B, and so on. Okay, so but it is understood from the context what it is, right? So that is why I'm using a mixture of notations so that like we are aware of the various conventions used. And H is the height of the center of gravity from the ground, okay? And WF and WR are the normal loads acting on the front wheel and the rear wheel respectively. So we can see that WF and WR are the normal loads acting on the front wheels and the rear wheels, okay? Now, what is this RA? RA is the lumped aerodynamic drag, okay, which is acting on the vehicle, okay? So RA, of course, as the vehicle moves, like there is going to be an aerodynamic drag, right? So RA is essentially the resultant aerodynamic drag experienced by the vehicle. So that is going to be assumed to be acting at this point and at a height of HA from the ground. Okay, so that is the aerodynamic drag. And typically, what we do is that like we lump the aerodynamic drag and we use it, you calculate it by this formula, half of rho A, CD, AF, V relative square. Okay, so what are these different parameters that come into the picture? Rho A is the density of air. Okay, so as we know, air is going to flow over the vehicle body, right? So, and the density of air is the local air density is denoted by rho A. CD is what is called as the drag coefficient. Okay, CD is what is called as the drag coefficient. AF is what is called as a frontal area of the vehicle, and VREL is the relative speed, okay, of the vehicle. So what is this relative speed? See, there may be a wind speed also, right? So we need to essentially consider the relative speed of the vehicle with respect to the wind speed. Okay, so that's why we consider it in this way. Okay, so this is the lumped aerodynamic drag acting on the vehicle, right? Okay, so that is one force. And then like we can see that there are these forces, the FBF and FBR. FBF and FBR are the brake forces developed at the front tire road interface and the rear tire road interface respectively. So the total brake force F subscript B is going to be equal to the sum of FBF and FBR. Okay. The total brake force is going to be the sum of FBF and FBR. Okay. Then if we look at this force, RD is what is called as the drawbar pull. So this will be considered when we are essentially pulling a trailer along with the vehicle, right? So if we don't pull any other entity, it's zero, right? So, but then like it's considered in general to derive the general equations, and we assume that lumped quantity acts at a distance of ht from the ground. Okay, so that is another thing. And we have these quantities RRF and RRR. RRF and RRR are what are called as the rolling resistance forces. Okay, so the total rolling resistance force at the tire rod interface is given by R subscript R, which is taken as the sum of RRF and RRR, and this is typically taken to be FR times W. Okay, so as a simple first cut approximation, it is taken to be FR times W. FR is what is called as a coefficient of rolling resistance, or the rolling resistance coefficient. Okay, so it is typically assumed that the rolling resistance at a particular tire rod interface is going to be proportional to the normal load acting on it, and the coefficient of proportionality is going to be equal to FR, right? So consequently, RRF can be written as FR times WF. R subscript RR can be written as FR times WR. Okay, so these are some essentially forms of the rolling resistance that we will be considering. Okay, and what is the physics behind rolling resistance? Okay, we'll come back to that free body diagram shortly, but let me first explain what is the physics behind this concept of rolling resistance. Suppose, let us say we consider a rotating tire. Okay, so of course at the tire rod interface, it's going to flatten. It's not going to be a circle per se. So there is going to be a contact patch, right, at the tire rod interface. And let's just say this is the center line. Sorry, this is the center line that of the central axis of the tire when looked at it from this side. Okay, and then now what happens is that, like, if we consider the tire rod contact patch, what happens is the following. Okay, so the normal stress distribution, okay, at the contact patch is going to be not symmetrical about the center line. Okay, so central axis. Okay, so that's what is going to happen. So consequently, the normal stress at the contact patch is going to look something like this. It is going to be asymmetrical above the central axis, and of course the wheel is rotating in this direction, and this is how the normal stress distribution looks like at the tire rod contact area, or what is called as the tire rod contact patch. And this creates a resistance force. Oops, sorry, I think there's some problem. 1 minute, sorry about that. Yeah, I think now the screen should be shared once again. Yeah, so this creates a net torque which is going to be acting in the direction opposite to that of rotation. Okay, so this is what is called as the rolling resistance moment. So once again, the normal stress distribution at the contact patch is going to be asymmetrical about the center line, and this is going to result in a moment that opposes the direction of or the rotation of the tire. Okay, and this moment is what is called as the rolling resistance moment. And why does this asymmetrical normal stress distribution arise in the first place? That's going due to the viscoelastic nature of the pneumatic tire. So there are hysteresis losses in the pneumatic tire, and that's what causes the asymmetrical normal stress distribution. and that in turn leads to this rolling resistance moment. Okay, and this rolling resistance moment, we can immediately observe that it's a decelerating moment. And when we want to realize it on the vehicle, we realize it as the rolling resistance force, RRF and RRR. Okay, so that is the physics behind rolling resistance. Okay, yeah. So moving ahead, the only other term which is remaining in this free body diagram, if I am not mistaken, is this W by GA. And what is this W by GA? It is essentially, we can immediately see that it's M times A, right? W by G is going to be M, right? So this is nothing but M times A, right? So, and we can see that we have drawn it using a dashed arrow. And the physics behind this is that although this is a dynamics problem, what we do is that we essentially draw this inertia force M times A, and we mark it in the direction opposite to that of the deceleration, which is along the direction of motion in this particular case. And we essentially are going to treat the problem as a quasi-static problem. And then we can balance all the forces along the direction of motion, and we will take moments about specific points and balance them to get equations of motion. Okay, so this is one way of getting the equations of motion. Okay, and when W by GA is written in this way and marked in this way, it is a pseudo force. It is what is called as a D'Alembert's force. Okay, so that is indicator of inertia. All right, so the reason why we are doing it, this is one common technique which we use in dynamics to get equations of motion. Okay, so where we essentially indicate the D'Alembert's force as a pseudo force that acts in the direction opposite to that of the acceleration or the deceleration, as the case may be. And then we treat the problem, the object to be in a state of quasi static conditions. And then we apply concepts from statics to get the equations for the dynamics problem. Okay, so that is the idea. All right, so that is why this is called as M times, the D'Alembert's force. This is a pseudo force. Okay, so that is something which we need to keep in mind. Okay, 1 minute, let me mark it with a curved arrow so that we don't confuse it with the direction of motion. Okay, so that is the D'Alembert's force. I think this explains all the forces that we see in this free body diagram, right? So for this particular vehicle during braking. Any questions on these forces and associated concepts before we move ahead?
Sir, for this rolling resistance, so this moment will depend upon how far this normal curve is away from the axis, right?
Yes.
So it will not depend upon the friction coefficient of friction of the surface.
So typically, analysis has shown that this rolling resistance coefficient depends on multiple factors, including the vehicle speed. Okay, and if you look at the tire road friction characteristics, I need to check, okay, whether rolling resistance has a very strong correlation with the tire road friction characteristics. But what I do know is that this FR has a good correlation to the vehicle speed. Okay, but for our analysis, we will take it to be a constant. Okay.
Okay, sir. Thanks.
This is once again an approximation. Okay, so we are only taking it to be directly proportional to the normal load and essentially getting a simple equation for that for first cut analysis. Yeah. All right. Okay, so let's move ahead. Any other questions? So before we move ahead.
Sir, what are typical values for rolling coefficient friction?
So it depends on various the tire construction and the composition. So what I am aware of is that for modern passenger car radials, it's an order of 0.01. Okay, yeah, but for truck tires, it's even around 0.006. Okay, so I will give you those values as homework during your homework problems. Okay. Yeah.
Okay, sir.
So those are typical values. So for passenger car tires, 0.01, 0.015, and so on are typical values. For truck tires, it's around 0.006. Okay, like so those are the typical values which people use. Okay. All right. So of course, rolling distance becomes very important, particularly for long haul operations, because it is a significant contributor to fuel consumption, right? So particularly for long haul trucks, in freight transport and so on, right? So particularly when people, tire companies, when they focus on manufacturing um, tires for these long haul trucks, they always focus on rolling resistance. But decreasing rolling resistance also has counter productive effects, which we'll discuss when we go to even like a discussion on ABS. All right. Yeah. Okay. So these are the various forces. Now let's go and balance out the forces and moments. Okay. So please remember that free body diagram. So what we are going to do is that we are essentially going to treat this as a quasi-static problem, and then we are going to write sigma fx equals 0 and take moments about points A and point B and then equate them. Okay. So that's what we are going to do. So let's do the derivation now. So the equation that balances the forces along the direction of motion, right? So once again, please note we are treating it as a quasi-static problem, right? So that's why we are using ideas from statics to get the equations of motion. So along the direction of motion, which is the longitudinal direction, right? So we are dealing with longitudinal dynamics. That's the direction of motion is the longitudinal direction. That is given by W by GA, which is D'Alembert's force, okay, or M times A. That's going to be equal to FBF plus FBR, and then plus RRF plus RRR plus RA, which is the aerodynamic drag, plus RG, which is the grade resistance. I will come to that shortly, plus the drawbar pull RB. Okay, so these are the various forces which is quite straightforward, right? Because W by G is A is along the direction of motion. All the others are in the other direction, right? So that's why we balance them out. Okay, so this FBF plus FBR is the total braking force, F subscript B, right? And this RRF plus RRR is the total rolling resistance, which is FR times W. And this grade resistance, what people do is that they will write it as plus or minus W sin theta s. Okay, so why this plus or minus? So theta s is taken to be an angle which is small. Okay, so consequently, when we are going up a gradient, we use this plus sign because it will be a resistance. When we are coming down the gradient, we use a negative sign because while coming down the gradient, W sin theta s is going to accelerate the vehicle, not brake the vehicle, right? So that's why we write it as plus or minus W sin theta s. I hope it's clear why we do it this way. Okay, so just rearranging the term. Yes, please.
Sir, frictional force also we forgot.
What is that? No.
Sir, the frictional force on the tires.
That is what is FB. Okay, we'll come to that shortly. Okay, yeah. All right. So when we discuss, get more into ABS, and so typically some people will write it as FX. Okay, FXF and FXR. We are just writing it as FBF and FBR just to indicate that braking force. Okay, so that is due to the tire road friction. Okay. So just rewriting this equation, we can immediately rewrite this as FB plus FRW is going to be equal to W by G times A minus RA minus RD minus plus W sin theta s. Why did it become minus plus W sin theta s? Because we are just taking it to the other side. Okay, so that's the just the rearranged equation. Okay, so this is one equation that essentially characterizes the translation along the direction of motion, the longitudinal direction. Okay, so let's call this equation as some equation number 1. Okay, so this is equation number 1. Okay, so now let us take moments about the two contact points, okay, A and B. So what are A and B? Please remember, A and B are the contact points, are the center contact, are the centers of the contact pads at the front and the rear tire rod interface, respectively. First, let's take balance the moments about point B. Okay, so that's something which we are going to do. So let us balance the moment about point B, which is the rear contact pad center point. So balancing the moment of various forces about point B, we get the following equation. So what is this equation? So we get W by G times A times H. Okay, so plus W cos theta S times L2. So those will be, if we go up, those will be two counterclockwise torques, right, about point B. Okay, so as we know, if you want to take the moment, we multiply the force by the perpendicular distance, right, or what is called as a momentum, right? So we are essentially balancing out the counterclockwise and the clockwise torques. So these two are the counterclockwise torques. All the others will be clockwise torques. Okay, so what are the other clockwise torques? WF times L, okay, capital L, plus RA times HA, plus RD times HD, plus or minus W sine theta S times H. Okay, so these are the moments. Of course, there is no moment above of the braking force and the rolling resistance force about point B. Why? Because those forces pass through point B, right? So the momentum is 0. So that's why we don't have moment of the braking force and the rolling resistance force. Okay, so that's something we do. Okay, now we are going to make some assumptions. We assume that the grade angles are small such that cos theta S is almost equal to 1. Okay, for small values of theta S. Okay, so these are all approximations that we are going to do. And we are also going to assume that HA is going to be almost equal to HD, which is almost going to be equal to H. Okay, so what are HA and HD? HA and HD, if you recall, they are the height of the points, height from the ground of the resultant aerodynamic drag and the drop output, right? We assume that both are almost equal to H. Okay, so we are just making these assumptions. So if we make these assumptions, cos theta S becomes almost equal to 1. HA becomes almost, we take it to be almost equal to H. HD also, we essentially take it almost equal to H. Okay, so these are all reasonable simplifications that we can do. Okay, so doing this, we essentially get the following. Okay, so we can rearrange the terms and we can get W by G A times H plus WL2 will be equal to WFL plus RA plus RG plus or minus W sine theta S times H. Okay, so this is what we have. So immediately we can rearrange the terms, okay, and we can get the following. Okay, so we can immediately get W, I'm missing something, oh no, W, that's correct. Okay, WF times L can be written as WL2 plus H times, we are going to do the following. Okay, so we will write it as W by G times A minus RA plus RG plus or minus W sine theta is, okay, so this is what we have. Okay, and what is this within the square bracket? The term within the square bracket is going to be equal to, from equation number 1, we can immediately see that this is going to be FB plus FRW. Okay, from equation number 1. Okay, so I'm sure all of us can immediately notice that, right? So we are just simplifying the equations. Okay, so now we can finally get the expression for WF. So what is the expression for WF? WF will consequently be equal to W by L, L2, okay, plus H by L, FB plus FRW. Okay, so this is a very nice expression, simplified expression for getting the normal load on the front tires. Okay, so of course, during this braking process, the way we have drawn the free body diagram, we have not made a distinction between the left and the right wheels, right? So please note that here we are denoting, we are looking at the vehicle from the side, and RRF will denote the total rolling resistance on both the front tires, because WF will be the total load on the two front tires. Okay, so please what to say, we have to be careful with the way the variables are defined in this derivation. Okay, so I'm just introducing various conventions to you so that like we know from the context how things are defined. Okay, so in this derivation, what we are doing today, WF is going to be the normal load on both the front tires, and WR is going to be the normal load on both the rear tires. So in a certain sense, we are lumping the two front tires and also we are lumping the two rear tires. Okay, so we are doing that during this analysis. Okay, so please let's keep that in mind. All right, so let's call this equation as some equation number 2. Okay, so this is equation number 2 as far as our derivation is concerned. So now I leave this to you as an exercise. You can just do it once again, and I'm sure you'll by now all of us know what to do. We take moments about point A. Okay, similarly, taking moments about point A. We just took moments about point B. Sorry about that. So we take moments about point A and just following a similar process. Okay, simplifying the equations results in the following. Okay, we get an expression for WR. So when we take moments about point B, we get an expression for WF, which is the normal load on the front wheels. When we take moments about point A and simplify, we get an expression for WR, which indicates the normal load on the rear wheels. Okay, so we essentially get a final expression which is of this form. Okay, WL1 by L minus H by L times FB plus FRW. Okay, so this is the final expression that we get. Okay, so now let's interpret this equation. Okay, so we are going to see something which is going to be very interesting coming out of this derivation, and then like we will also use it to understand some physics of the braking process also. Okay, so let's call this as some equation number 3. Okay, this is equation number 3. Now, in fact, if we look at a static vehicle on a flat ground, okay, so I'm just going to draw a very simple diagram. Let's say we have a flat surface, and then like I have the front wheels and the rear wheels. Okay, I'm just going to draw a very simple diagram. So let us say this is the car or the vehicle under study. Okay, and let us say the total weight is W, which is acting at this point. Okay, so this is W, this is the CG of the vehicle, and the vehicle is moving. Of course, the vehicle is stationary, right? So this is the front and this is the rear, right? So let's mark WF and WR. Okay, so WF is here. Sorry, this is the normal load. Okay, so this is WF and this is WR. Okay, WR is the normal load acting on the rear wheels. Okay, when the vehicle is static. Okay, and as we know, the distance between the front wheel and the rear wheel center is the wheelbase L, and the distance of the CG from the front wheel center is L1, and the distance of the CG from the rear wheel center is L2. Okay, so these are things that we are already aware of. Okay, so now if you consider the static condition, okay, so let's see what happens. Okay, so consider a static vehicle on a flat surface. So we know that W is going to be equal to WF plus WR, right, from this particular equation. And we already have derived things, right? So let's say this is point A, this is point B. Like we already know that if we take moments about A and balance them, what are we going to get? We are going to get WR times L minus W times L1 is going to be equal to 0. So consequently, WR is going to be equal to W times L1 by L. Okay, so this will immediately imply that WF, which is W minus WR, that's going to be equal to WL2 by L. Okay, I think we have already discussed this and we are aware of this, right? So these are the essentially the loads acting on the front and the rear tires of a normal loads acting on the front and the rear tires of a static vehicle. Okay, so that's what it is. Okay, so now things become interesting, right? Why? Because we can immediately see something interesting coming out of it, right? So let me write down the two expressions, what to say, that we derived for the dynamic case. So going back to the case of braking, right? Our analysis of braking, okay, we just derived WF to be equal to WL2 by L plus H by L times FB plus FRW, and we derived WR to be equal to WL1 by L minus H by L times FB plus FRW. Okay, so this is what we derive. All right. Okay. So of course, if we add the two expressions, we get W, obviously, right? So we should get the total weight of the vehicle, right? So that is understood. Okay. But we see something very interesting coming out, right? So what is that interesting aspect that we can observe? We can immediately see that the first term on the right hand side of both equations, right? This equation and also the other one, we can see that for WF it's WL2 by L, for WR is WL1 by L. We can observe that they are exactly what we derived here, right? For the static vehicle. Okay, so for the static vehicle, we got the static load to be WL1 by L on the rear wheel, and for the front wheel we got WL2 by L. Okay, so we can immediately see that these two components are the static loads on the front and the rear wheels respectively. Okay, that's the first term on the right-hand side of both equations. Now, what are these two components? We can see that the second component on the right-hand side of both equations are equal in magnitude. Okay, so they are essentially H by L times FB plus FRW. Okay, so the magnitude of the second term is the same. Okay, however, what is different is the sign. We can observe that this H by L times FB plus FRW is added to the normal load on the front wheel while it is subtracted from the normal load on the rear wheels. Okay, so these are the dynamic load components. Okay, so these are the dynamic normal load components, and this is essentially what is called as dynamic load transfer due to braking. Okay, and that is something which all of us have experienced, right? So let us say we go in a car, right, and there is a a severe braking scenario, right? What happens to all of us? We tend to go forward, right? So that is because due to the inertia, right? So we essentially tend to move forward, but there is a braking motion that is happening, right? So consequently, what happens during braking is that there is a dynamic load transfer, normal load transfer that takes place from the rear to the front. Okay, so this component is essentially the dynamic load transfer that happens due to braking. Okay, so this is the longitudinal load transfer during braking. Okay, so that is why this component of the normal load is what is called as a dynamic component or the longitudinal load transfer component during braking. We will see that while we derive equations, similar analysis for the drive motion, that is during acceleration, the reverse phenomena is going to happen, right? So when we essentially brake the vehicle, we are going to see that the dynamic load is going to be transferred from the front wheels to the rear wheels. Okay, so that's what will happen during acceleration. Okay, this is what is going to happen during braking. And now I think we can connect it to our discussion on drum brake and disc brake, right? So even in the previous class when we discussed that when we brake, right, the normal load on the front wheels will become higher. I'm sure from today's class we have understood how it happens, right? The physics and also the mathematical equations behind that. So consequently, when the normal load on the front wheels become higher, there is more capacity for braking on the front tires, and that is why we want the brake on the front tires of a typical passenger car to be more reliable, because a greater proportion of the braking will come from the front tires, not only due to the static load but also due to the dynamic load which happens due to this longitudinal load transfer during braking. So that is why we use disc brakes on the front and drum brakes on the rear as a via media solution, right, in most passenger cars. Okay. So I hope this discussion, this derivation and the corresponding physical interpretation are clear. Okay, so any questions on these? Okay. So yes, yes, please.
Sir, actually, the drum brake will have more force, braking force than the disc brakes, as you highlighted yesterday, right, sir?
Correct. So, if you give the same, if you give the same actuation force, the drum brake friction force output will be more than the disc brake braking force. No doubt about it. Okay, because the brake factor of the drum brake is greater than the brake factor of a comparable disc brake. Okay, the main challenge was because the brake factor, the drum brake had greater mu sensitivity, okay, when compared to disc brakes. That is why we don't mind the higher size and expense. We go for more reliability, okay, on the wheels where there is a greater potential for braking, which happens to be the front brakes in most passenger cars. Okay, that's why we put disc brakes there.
Sir, if if in case there is a drum brake in the front, then since the weight transfer is happening to the front, we get a higher braking force, and can we reduce the stopping distance as well then?
Okay, that's a good point. So the stopping distance is dependent on two things. Okay, one is the actual foundation brake that we put on the vehicle, right? The brake subsystem, and also the characteristics of the tire rod interface, which we are going to study in the next class. Okay, so even though our brake unit, disc brake or drum brake, may be designed to generate a very high braking force, there is a limit on how much force can be sustained at the tire rod interface along the longitudinal direction. Okay, we will study that aspect. That's a good point. Okay, so that's a nice way to look at this problem also, because what Ratish is saying is that, like, okay, if we put drum brakes on the front, due to dynamic load transfer, I'm going to get more brake force. But is that really going to help us? We are going to learn, okay, in the upcoming classes. All right, yeah. Okay, any other questions? Okay, so in fact, that is exactly what we will study in the next class. Okay, so I will stop our discussions here, and then I will continue from here in the next class. We are essentially going to figure out what is the maximum braking force that can be generated at the tire rod interface, and then how do we distribute the braking force at the front and the rear wheels, so that we can then use that brake force distribution to size the drum brake and the disc brake. Okay, so that is an analysis which we will do in the next class, following which we will also do an analysis of under what conditions would we have what is called as wheel lockup, okay, on different surfaces. That will naturally motivate us to learn about anti-lock brake systems. Okay, so those are the upcoming topics that we are going to see in braking dynamics. All right. Okay. Any questions? Yeah.
So this plus minus W sine theta term we are taking because of braking on incline and decline, is it?
Correct. Exactly. Okay. So without loss of generality, we are considering motion on an inclined road. Okay. So if we are going on a flat road, that term will be 0.
Okay, sir. Sir, this dynamic load transfer term, sir, will it be dependent on like the suspension or anything?
Okay. So, okay, that's a good point once again, right? So, in this discussion, we have neglected suspension dynamics. Okay, so there is going to be a component which will come in because of suspension dynamics also, right? So, if you look at this entire derivation, I have not modeled the suspension, right? So we'll come to that later on, right? So not only will there be some pitch dynamics coming into play during braking, because we can see that, right? While braking, there's a pitch motion, right, which happens, correct?
Yes, sir.
But not only that, there can be a vibration due to the road characteristics, which can also come into play, right? Is it not? There can be road perturbations, right? The road is not going to be smooth, right? We are going to have roughness, road roughness, which will come into account, and that may create some variations in the normal load, right? So yeah.
So currently,
Good.
like we are infinite stiffness in this.
Yeah. So right now we are not considering the effect of suspension. That's a good observation. Yeah.
Okay, sir.
Yeah. Okay. So if there are no further questions, let me stop today's class here. Thank you.